ring into a Q-commutative Laurent polynomial ring. So this means that for any two variables, xv and xu, then xv times xu equals q to the power of an integer and times xv. Yeah. It's just two variables are Q-commutative. They're not commutative. So this is the quantization of the Teichmüller space. But now for this talk, it is for the SLN quantum Teichmüller space. It just means, I mean, the classical Teichmüller theory is for SL2. So this is just a generalization. And I mean, there are two quantizations for this SLN Teichmüller space. So one is the SLN skein algebra. Another one is a quantum torus. And there's a very important map called the quantum trace map connecting these two quantizations. So today we're going to look at the representations of these two quantizations. Okay, so first let's look at the definition of the SLN skein algebra. So the SLN skein algebra of a surface S, this symbol is S, of a surface S was introduced by Adam Segura as a quantization, just like I said, of the SLN capital variety. So, I mean, if you're not familiar with the capital variety, that's okay. So anyway, this home set is the set of all the group homomorphisms from the fundamental group to SL to C, and that will quotient by taking the trace, or maybe a little bit cheating if I say taking the conjugation. That's also okay, I think. So if you are familiar with the Teichmüller space, then you will see that this thing is very like the Teichmüller theory. If we replace this SL in C with the PSL2R, and then we will get the Teichmüller space. And in this talk, we will work with the punctured surface. And a punctured surface is obtained from an oriented closed surface by removing a finite set of points. The definition of the SLN skein algebra uses in-webs in the thickening of the surface. The thickening of this surface just means we use this surface and then we times the open interval, and then we will get a 3 manifold. So by the way, if you have any questions, please just interrupt me. So now we look at the definition of the in-web. So an in-web in the thickening of the surface is a disjoint union of framed oriented nodes and embedded framed oriented graphs, such that each graph contains only infinite sinks and sources. So we have two different types of components. So one type is the circle. It is oriented circle and also with framing. If you are not familiar with the framing, you can just forget about the framing. Just forget about the word frame. So that's okay. Another component is the graph, oriented graph. But this graph is very special. It only contains invariant vertex, just means for every vertex, there are n edges connecting to this vertex. And also for every vertex, it is a sink or source. It just means for every vertex, all the edges coming to this vertex, or all the edges just leaving this vertex. And then this is the definition for this in-web. Yeah, and here there's an example for the 3-web. It just means n is 3. You see then we have 3 components. 2 of them are nodes. One of them is the graph. And here we have this is a sink. This is a sink, yeah. This one is the source. So, yeah. Any questions with the definition of the in-web? This is very important for this talk. Okay. So for today, we will just work with the complex field. So normally you can define the SLN skein algebra over any domain. But today, we just focus on the complex field. To define the and skein algebra, we need a quantum parameter. It just works because just like I said, it is the quantization. So we need a quantum parameter. So let this guy to be a non-zero complex number, and we define the omega bar to be omega hat to the power of n, and omega to be the omega bar, no, omega hat to the power of n squared. And also we have these two notations or two conventions. The SLN skein algebra of a surface S, a punctured surface S, is the quotient module of the C module or the C vector space, freely generated by the set of all isotopic classes of n webs in the thickening of the surface, and then subject to some relations. So maybe let me briefly explain the isotopic class. Two n webs in the thickening of this surface are isomorphic to each other if and only if we can smoothly deform one to another. Everything is smooth. And then we consider all the n webs up to isotopy. It just means if two webs are isotopic to each other, and then we just regard them as the same web. So we just use the isotopic class of the n webs as a basis to generate a C vector space, and then we just put in some relations. They are local relations. Now let's look at these relations. We have four relations. Okay, let me explain how to understand these relations. So these relations are local relations, and this gray square is the projection of an open cube. An open cube is just this square times a very small open interval, and we just project the pictures inside of this open cube to this open square, this gray open square. For example, for the first relation, we have three webs. Maybe first web is L1, second one is L2, and the third one is L3. And then outside of this open cube, all these three webs, they're identical to each other. And inside of this open cube, L1 is look like this, L2 is look like this, and L3 looks like this. So, and also this relation just means this complex number times L1 minus this complex number times L2 equals to this complex number times L3. This is how we understand the relation. Yeah. And for the other two relations, just understand this in the same way. Or you can just think of that. So we use the webs as a basis to generate a free vector space or a vector space. And then we question some local relations. These relations, I mean, they're just defined using four pictures. Yeah. Any questions with this relation? If you have any questions, please just ask. Please. The difference. The difference is just inside this gray square. For example, I mean, the second one, the crossing.
Second line.
Certainly this one. Because now we're using the framing. The framing is what? The framing means it is not a line. It is a thickening of this line. You just think, so this is, you can just regard this line as a band. It is a band. So it is a band. You have the thickening. It is a band. So if it is a line, of course, this one is isotopic to this one. But if you have the framing, for example, if this is the band, and then this guy is not isomorphic to this guy, you can just do this with a paper. You say, if you have a paper and you do this, you cannot just straighten up. So actually, this one is different with this. This is why the framing matters. Okay. Yeah, good question. Thank you. Okay. Now I only show the three relations. So we have the first one. And the first one is a little bit complicated, but I can say something about this relation. The first relation involves a pair of sink and a source, and also we can use the first relation to kill all the sinks and sources of the in-webs, and then the skein algebra is spanned by the links, by the framed links. This is the definition for skein algebra. Any questions with this? Okay, let's continue. Okay, sure. Yeah. For general SLN, I guess the answer is no. We still don't know how to. I mean, we can find the generators. For example, just like I said, all the nodes, or maybe all the links, that the algebraic generators, or the framed links. But this is not good. This is too big, right? Too large. I mean, actually, we believe that the SLN skein algebra should be finitely generated by something. But this family, I mean, the family of the framed links, this is not finite. But for SL2 and SL3, now people already proved that, I mean, this SL skein algebra, it's finitely generated by something. Yeah, we can just use the, we can use something called the webs corresponding to the, because for SL2 and SL3, we have the basis, and also all the bases have the coordinates, and all the coordinates, they form a monoid. They form a monoid, monoidal or monoid. I forgot the pronunciation. Okay. It forms maybe not a group, but without the subtraction. And this thing has a basis, something like a basis, not a real basis. And this guy is finite. And then every links or every webs corresponding to the elements in this basis, all these webs that the algebraic generators for this SL skein algebra. Yeah, when n is 2 and 3. Yeah. Yeah.
And so, but in your data, I cannot see the relation.
The generators.
Generators and for example, you said SO2 and SO3.
Yeah.
If I change to SO2N, SO2N and or SE2N, I mean,
you mean
what's the data of group in your application?
You mean the data for what? For the group?
Yeah.
You mean SL in this group?
Yeah. And you change SO2 to ST2.
No, I don't think. I mean, so the aim plays the role here. This number is for n.
What's the why do
SL. I see. I guess the SL comes from the, so for example, so why, yeah, that's a good question. So why this is for SLN? I mean, not for some other n, for example, SP, SPN. So because all these relations, they come from the representation theory of the UQ SL1. So why we have this relation? Because these relations, they come from the representation category of the UQSL1 for this quantum group. Yeah. This is why this is for SLN, not for SPN or some other group. Yeah, sure. That's a general definition for all the D group. Semi-simple. Yeah, just change the rules. But for other D group, we don't know how to use the pictures to define the skein algebra. Yeah. I mean, for example, for S7, we know the pictures, but maybe for some other general semi-simple Lie group, we don't know how to use the pictures to define the skein algebra. I mean, so there's a general technique for us to define the skein algebra of any semi-simple integral. Yeah.
PGL.
PGL, actually, it is not semi-simple. It is not semi-simple. But I think there's a definition for this.
I think what's one way of understanding is that each picture in the square as representing a morphism in the representation category, where in this case the strands they stand for the tautological n-dimensional representation of SLN, UQSLN. So there are different models that involves more representations, other fundamental representations of UQSLN, but this version uses only the n-dimensional tautology.
Yeah.
So if you consider other quantum group or other Lie group, then you have to come up with some generator of the morphisms. And then these are the relations between different worlds.
Yeah.
So you might have to have not just one kind of strand, but many different kinds of strands. I don't know what to say about PGL.
I think there's also a definition for this, for at least for GL1. Maybe. For GL2, at least we have the definition. Okay, yeah. So for this guy, this is just the R matrix, and this one is the inverse of the R matrix. This is the identity. So this relation just means in the representation category, this complex number times the R matrix minus this complex number times the inverse of the R matrix equals to this complex number times the identity. You can check this. This is true in the category, in the representation category of UQSLN. I mean, of course, maybe this should be the R matrix for the fundamental representation. We use the n-dimensional representation, a reducible representation. Yeah, okay. So this is the definition for SLN scales. Still, we need a product because this is the algebra. So then for any two n-webs, alpha and alpha prime in the thickening of the surface, then the product of alpha and alpha prime is defined by stacking alpha over alpha prime. I think the definition is easier to understand. So here it is the explanation. If alpha lives between 0 and 1, and alpha prime lives between -1 and 0, and then the product is just given by taking the unit. So when we take the product, we just push alpha to the upstairs, and then push alpha prime to the downstairs, and then we take the disjoint unit. This is a well-defined product. And also for the n-webs, we allow empty web. It just means nothing. It is empty as a set. And you can easily see that the empty web is the identity in this algebra. Okay. I should speed up. So now let's look at the quantum drift map. To define the quantum drift map, we need the ideal triangulation. An ideal arc is an embedded arc in the surface connecting two punctures. A triangulation, lambda, of a surface is a collection of disjoint ideal arcs in the surface, such that we get a collection of triangles after cutting the surface S along all the arcs in lambda. This is the definition. Here is an example for the triangulation of the once punctured torus. Of course, not all the surface have the triangulation, but we don't care about this. We just assume in this talk every surface has a triangulation. Okay, so if we have the triangulation, so just like I said before, to define the quantum drift map, the targeted space is a quantum torus. So to define quantum torus, when you know an anti-symmetric, an integral anti-symmetric matrix, or it is the same to define a quiver. So now let's look at how to get a quiver or how to get an anti-symmetric matrix to define the quantum torus or the target space. Okay, so S is a punctured surface with a triangulation lambda. We use F lambda to denote the collection of triangles obtained by cutting S along all the ideal axes of lambda. Then we'll get a collection of triangles. We use this gamma lambda. So this gamma lambda is a quiver on the surface S such that for each triangle tau, in this collection, and then the intersection of this guy, maybe I should say the interior looks like this. Anyway, so the intersection of this gamma lambda and this tau is given by this picture. So for every triangle, it looks like this. Of course, it's possible we have another one because this is just a look picture in one triangle. This is the picture for n is 4. Then you can imagine the picture for general n. Another way to understand this quiver is that for every triangle we have this, because we can glue all the triangles. We can glue the triangles to get the surface S. And then you just glue all the quivers together. And such that when we glue the quivers, such that all these vertices of the quivers, they match together. And then you will get a big quiver. And then this quiver is on S. Any questions with this quiver? Okay, let's continue. So now we have a quiver. And then we can define anti-symmetric matrix, just the assigned adjacency matrix of this quiver. And we use V lambda to denote this vertex set of this gamma lambda for any two vertices V and V prime. And this A lambda V prime is the number of arrows in gamma lambda from V to V prime. It's easy to understand. And then the anti-symmetric matrix is defined using this formula. So this is of course, it is an anti-symmetric matrix. Also, it is integral matrix. Yeah. Okay, now let's look at the definition for our target space for the quantum torus. Actually, this one is not a target space, but it is related to the target space. The Goncharov algebra is the quantum torus algebra defined as follows. So you say it is something like a Laurent polynomial, but this xv and xv prime, they're not commutative. They're something like Q commutative. Of course, now we're using omega. Yeah, and also it's Q or omega commutative information or the data is determined by this anti-symmetric matrix. So this is why we need this anti-symmetric matrix. Actually, this definition is a general definition for the quantum torus associated to an anti-symmetric matrix. To define the quantum trace map, we need a slightly bigger algebra. It's called the ancient root Goncharov algebra. So the difference with the previous one is that here the generator is labeled by Z. You can see that. And the important thing is this is here. Here we use omega hat. But for the first one, for the X, we use omega. So this is the difference. Yeah. Of course, to distinguish the generators, here we just use Z for the variable. So why I say that this Z is bigger than X. So here is the reason. So recall that omega is omega hat to the power of n squared. And then there's an algebra embedding from this X torus to Z torus given by this. It sends XV, it maps XV to ZV to the power of n. You can easily check it is very defined. Because you see for this Zn, if there's a power n, if there's another power n, and then here will become omega hat to the power of n squared. So this is why here it is n squared, but here is n. If there's a power n, if that here is a power n, and then here for the omega hat, it will be the power of n squared. So this is why here is n squared. And using this, so with this embedding, we just can regard the x terms as a subalgebra of the z terms. So this is why I say that z is bigger than x. Okay, any questions with this slide? Okay. Okay, now let's look at the quantum trace map. So S is a punctured surface with a triangulation lambda, and then there exists an algebra homomorphism from the SL skein algebra to the Z terms. Until now, we don't know whether it is injective for general n, but people proved that it is injective for SL2 and SL3. So why this quantum trace map is interesting? Because just like I said, we expect that it is injective. So one obvious thing is that if we can prove that it is injective, it is well known that this guy is a domain. And then we can prove this guy is a domain. But now we cannot prove this for general n. Another important thing is that also for SL2 and SL3, there's a basis for this guy. And the basis behaves, all these basis elements, they behave very well. Under this quantum trace map, especially the highest term. And then the highest terms we call the coordinates of the basis elements. We can use this to calculate the center of the SL skein algebra, and also we can study the representation area of the SL skein algebra. This is why the quantum trace map is important. Yeah. But it is not easy for me to explain, how to define this map or how to calculate the image of the quantum trace map. It is very difficult, actually. You just keep in mind that there exists such a map. Yeah. Okay. Actually, the image of the quantum trace map is contained in a slightly small algebra of the Z quantum terms. So now I'm going to explain. This slightly smaller algebra called the balanced part. So before that, let me first introduce some definitions. We first order the vertices in V lambda by this. And then for any vector key, we define the monomial like this. This is called the well normalization. So there exists a subgroup B lambda of this guy, consisting of vectors in this abelian group, satisfying some equalities, and with this property. So one important property for this subgroup is this. It is not so easy to explain the definition of this subgroup. You just keep in mind that we can define this subgroup using some equalities, collection of equalities. And another important property is this inclusion. It just means, okay, you will see later, this X is contained in this subgroup, in this subalgebra. So now we have a subgroup. We call this subgroup the balanced part. And then we will use this subgroup to define subalgebra of the Z terms. So Li and Yu defined the balanced for Goncharov algebra by this. So this subalgebra is bound by all the Z to the power of key, such that key lives in this balanced subgroup. And because V lambda is a subalgebra, you can easily prove that actually this guy is a subalgebra. The balanced part is a subalgebra of the Z quantum terms. and it was proved by Li and Yu. The image of the quantum trace map is contained in the balanced part. And also in this talk, I will study this balanced part, the center of this balanced part, and the representation theory of this balanced part. Any questions with the definition? You can ask a little bit about this V, but I cannot explain the definition. It's too complicated. Okay, cool. So let's continue if no questions. Let's look at the center. First, let's look at the center. Okay, so first let's look at some central elements defined for each puncture P. Actually, for each puncture P, there are n-1 central elements in the balanced part. Okay, so for each puncture P and an integer I between 1 and n-1, we define a vector A by this. So what is AV? So AV is the number of times of the vertex V appears in the line at a distance I from P. So what is the line at a distance I from P? So here, let's look at this picture. Of course, I mean, this is just a picture for a special case. It is possible that you have more than 3 lines connecting to this puncture. This is just for a special case. The distance 1 line is this blue line. Is this blue line? You can see that why it is called distance 1 line. Yeah. The distance 2 line is the red line. Also, you can see why we call this distance 2 line. And then the distance 3 is this green line, and then you just keep going. You can have the distance n-1 line. I mean, maybe we go back to the picture for the quiver. You can see that. So it just means this guy, if we look at this puncture, the top one, and then this is the distance 1. So, and then we go to lowest there, distance 2, distance 3. So it is very clear for the distance. So,
Scheme algebra, as you mentioned, is a kind of quantization.
yeah.
Capture point.
What? It is quantization. Yeah, capture writing. Yeah, capture writing.
Because I'm not familiar with this.
Maybe back to the older time. I guess maybe, I think even now, some people call the skein algebra as the generalization of the joint polynomial to the 3-manifold. I think maybe this is the first motivation. The joint polynomial is defined for the R3 or S3. So it is just for 1 manifold. And then we generalize this definition to general 3-manifold. Just cross the skein relation.
So we know there is a non-linear algebra based on capture items, one as aging system. And so since on one side you introduce the quantization of the capture idea, which is skein algebra.
Yeah.
Is there any known results of using this non-linear algebra theorem and this kind of quantization to relate something to the model space of Higgs bonders on the other side? You know, such kind of.
No, actually, I'm sorry, I'm not familiar with this. Do you know anything about this? Okay. Yeah, thanks for the question. Okay, so now we have the vector A.
Also, we have other questions.
Okay, sure.
So, is there any that this kind of skein algebra can act on the homology agreement kinds
Act on the capture radio.
homology agreement? You know, such kind of like geometry representation theory.
Geometry. I don't know.
You have never seen anything like that.
But even there is no such kind of expectation.
I have never heard anything about it.
Or do you know any results like the skein algebra can act on certain cohomology of certain variety or?
I think I should say no at this point. I can tell you something that might be related, at least not directly related yet.
Sorry.
Okay, sure, that's okay. Okay, now let's continue. So now we know the vector A. Okay, AV. So it is the number of times V appears on this line. So why it is the number of the times? Because it is possible that, it is possible that there's some identicals between these vertices. For example, look at this red line. It is possible that this vertex is identical to this one. Maybe this example is not good. If we do not allow the self-folded triangulation, then this is not a good example. But anyway, there could be some repetitions among these vertices. It is possible that this guy equals to this guy if we have some other more lines connecting to this vertex. So this is why we use this, the number of times this V appears in this line. So it is possible that the AV is 2. I guess the maximum is 2. Yeah. Okay, so this is the definition for the vector A. But a better thing is that A is not contained in the balanced form. So now we need a vector contained in B lambda. So this is why we define this vector B using the vector A. So this is the definition for B lambda PI. You see, the B lambda PI is the linear combination of B lambda PT. For T from 1 to n minus 1. Yeah. And we can show that this B lambda, this vector B is contained in the balanced form. So this is good. And we will just use this B to calculate the center of this, the balanced for Goncharov algebra. Okay. So here's a proposition. So let S be a punctured surface with a triangulation lambda, and P is the set of the punctures of S. Suppose that omega is not a root of unity, and then the center of the balanced part is the polynomial ring generated by Z to the power of B for all this B, for all this vector B. So this is for the case when omega is not a root of unity. And later on, we will look at the case for the root of unity. Actually, now root of unity case is not so interesting. The root of unity case is interesting, especially for quantum torus. Because for non-root of unity case, the center is too small. Okay, now let's look at the root of unity case. So here is the convention for the root of unity case. This guy is a root of unity such that the order of the omega hat square is n double prime. So this is our definition. We defined this actually, or we already introduced this omega bar and omega. And then omega bar square has order n prime. This is the definition for n prime. And then omega square has order n. The n equals n prime of d. This is d. D is the greatest common divisor between n prime and n. And here we set this complex number, this omega, this eta bar, to maybe the square root of eta bar to be this. This here is the capital E square. And then we have this, and then the omega, not omega. And then similarly, we can define the eta bar and eta. This is just the convention. You don't have to remember this clearly, just have a rough picture, then that's okay. Okay, so now let's look at some other central elements with this root of unity assumption. So under the root of unity assumption, we have the following algebra embedded. It is from this, you see, this is the z terms for eta. This is the z terms for omega, different. Quantum parameters are different. It sends z to the power of k to z to the power of n k. Here k is a vector, And for any two vectors, k and t, it is well known that we have this relation. You can calculate this easily. And then if we add a power n to this k, of course, k and t, they're balanced vectors. K and t are balanced vectors. So, and then we have this relation, because now it is n times k. So here it is n times k. I have this. So we know that this guy is a root of unity. So this omega bar to the power of 2n is a root of unity. So let's look at its order. The order of omega bar to the power of 2n is d times this guy. Yeah. And then we define this b lambda d to be this subgroup of b lambda. It's just for all k in b lambda such that q lambda t transpose is 0 in zdn. I mean, so this is just the product for vectors and matrices. We just regard this as the row vector. So this is the definition for b lambda d. So let's say if k is in b lambda d and t is in b lambda, then we can then you say the order of the omega bar to the power of 2n is d times this greatest common divisor. And also the product of the vectors and the matrix, they are the multiple of dn. This is the definition, and the multiple of dn. So this means here is 1. Here is 1. So then we get this. It just means z to the power of nk is central. Is a central element. So now we have this. This guy is central. So, and then naturally we can just define this subalgebra of the z torus for eta. I mean, it's labeled by this d. It defined with this. It is bounded by all the z to the power of k, such that k is in the b lambda d. So from this argument, we know that this map phi, I mean this map, the Frobenius map, this map phi maps all the elements here, into the center of the z of the balanced part of the z quantum torus for the omega. I mean, it just phi maps this guy into the center of this one. This we already showed this. Z to the power of nk is in the center. Because the definition is that this guy maps to zk to the power of nk, to the power of, it maps zk to z to the power of nk. So now we have for unity case, we have two different central elements. One is one is associated to a puncture. Another one is the image of this guy. And then this theorem tells us that actually for the root of unity case, the center is generated by these two different types, two different central elements. Suppose that omega hat is a root of unity and S is a triangulable puncture surface with a triangulation lambda. Then the center of the balanced part is generated by this, by the central elements in the Frobenius map, and by the central elements related to the punctures. So this is the whole center. So why it is important to study the center? Because later on we will see that we can use the center to study the representation theory of the balanced Fock-Goncharov algebra. Because if the center is big enough, then the irreducible representations of the algebra are almost uniquely determined by the action of the center on this irreducible representation. Almost. So this is why we study the center. Okay. Oh, here's another one. This is the rank of the balanced Fock-Goncharov algebra, of the balanced part. Still, we have the root of unity assumption. So S is a connected punctured surface with a triangulation lambda. And then the balanced part is a free module over its center and of this rank. This is the rank. So here, so D is the greatest common divisor between M prime and small n. M is the number of punctures of S. G is the genus of the surface. So this is the rank. So also why we study this rank. Later we will see that all the irreducible representations, you see this rank is a square. This rank is a square. Later we will see that all the irreducible representations of the balanced part have the same dimension. Of the square root of this rank. So the square root of this rank is just the dimension of the irreducible representations of this balanced Fock-Goncharov algebra.
Can I ask you?
Sure.
In the case of the genus one, what happens?
Genus one. You mean if it is genus one, what is this dimension? Yeah, and just if it is genus one, then it is just D square, and then times n to the power of the capital N to the power of n times n minus 1 times m. For genus 1, just replace this G with 1. Here will become 0. So we only have this, and then here is D square. So it is always a square. Because here we have a 2, here we have a 2. Here is n times n minus 1.
Where's the number?
Pardon?
Where's the number to triangulation?
A triangulation. I mean, so the triangulation is not here, but the number of the edges of the triangulation is determined by the G and the M.
This rank is independent of rank.
Yeah, this rank is independent on the triangulation.
Yes.
Yeah, thanks. So now let's look at the representation theory for the balanced part. So let's rho to be a finite dimensional irreducible representation of the balanced part. Still, we have the root of unity assumption. Then for n x in here, and then for n x in here, then we have this phi x is in the center of the balanced part. So it just means rho maps this element to be a scalar multiplication. It just means there's this R rho x such that this is true. This is the Schur's lemma. Also, this guy is also a central element. And then rho maps this central element also to a scalar multiplication, which means we have a BPI times this. It is scalar multiplication. So, and then we look at the relation between this R rho and this complex term BPI. Any questions with this? Okay. So we can either show that R rho is an algebra homomorphism because rho is an algebra homomorphism. R rho is it's just some algebra homomorphism from here to here to the complex field. For every integer I between 1 and n minus 1 and puncture P, we have this equation. So this means that our rule maps. I'm sorry. Here we should just remove this capital N, and we should remove this capital N. I'm sorry. Yeah, we should remove this capital N. There's no this capital N. So this just means our rule maps this z to the power of b equals to this. This is the relation between our rule and then this complex number b pi. Yeah. We remove this capital N here. So you see now for each irreducible representation of the balanced part, we have two data. One data is this algebra homomorphism R rho. Another data is this BPI. And these two data are related by this relation. Remove this N, capital N. So, and then a natural question to ask is that if we have two sets of data, can we find an irreducible representation of the balanced part such that this irreducible representation gives us this data? So actually the answer is yes. So S is a connected punctured surface, genus G and punctures. Also root of unity, we have the root of unity assumption. F is an algebra homomorphism from this guy to C, and also we have the complex numbers. Actually, I mean they are not zero. Actually, I mean from the definition of this B, you can understand why it is not zero, because this guy is invertible. It is a long-range polynomial. It is a monomial. It is invertible because this guy times z to the power of minus b is 1. This is why this guy must be non-zero complex number. And also we have non-zero complex number BPI such that BPI to the power of n equals this. So the relation between these two data. And then there exists a unique irreducible representation rule for the balanced part such that R rho equals to F. And also for every central elements related to the puncture, we have this equation. And also the dimension of V is this guy, the square root of the rank. So, I mean, you can see that all the irreducible representations of the balanced part are classified by these two, by these two data. Okay, so now let's look at the representation theory of the SL1 skein. I will try to speed up a little bit. Okay, so for every puncture P, I think maybe we have 6 or 7 slides left.
You have plenty of time.
I have plenty of time. Okay, if so, then we'll just keep it the normal speed. Let P, because I'm afraid of that some people are hungry. So let P be a puncture. Let P be a puncture of S, and K is an integer between 1 and n minus 1. And then there's n web alpha pk in the surface. I mean, in this S. So this is alpha pk. This is this n web. This is the picture for this n web. Actually, I mean, you can easily prove that it is in the center of the SL skein algebra. Why? Because it lives in a very small neighborhood of the puncture. For example, if you have another web W, you can always isotope W such that W, there's no intersection between alpha pk and W. And then, so this is W. So then this is W times alpha pk. Because there's no intersection between alpha and W, you can just isotope this. And then it will become alpha times W. So this means W times alpha pk equals to alpha pk times W. Because there's no intersection between W and alpha pk for any W. So the alpha pk is a central element.
Okay, let me ask you about
Sure.
your data. Now you have the without genus.
Yeah.
Okay, and then
Here.
you can set up this kind of thing. You set up on this one without the genus.
Yeah.
And then you can get this kind of data.
Yeah.
Okay.
Yeah, yeah. Okay. I mean, when I say the data, it just means this algebra homomorphism F and this BPIG. The genus only plays the part to determine the dimension of the irreducible representation. Okay, so now we have this alpha pk. Okay, just like the balanced part or the balanced Goncharov algebra. So we have the Frobenius map phi. For the, I mean, no, I'm not yet to introduce the Frobenius map. Let me first look at the SL1 Chebyshev polynomial. Okay, later on I will introduce the Frobenius map for SL1 skein algebra. Before that, let's look at the SL1 Chebyshev polynomial because we will use this to, I don't want to say define, I will use this to introduce some properties of the Frobenius map for SL1 skein algebra. We use this EK to denote the case elementary symmetric polynomial in the variables xi. Of course, but this EK lives here. I mean, it is not this polynomial ring. We constant this. The product of x1, blah, 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 xn is 1. It just means the nth elementary symmetric polynomial is 1. And then for each positive integer m, it is well known that there exists a unique polynomial bar, so bar p, so a p bar nk, such that we have this equation. You see here, inside this big bracket, this is a symmetric polynomial. So it is well known that elementary symmetric polynomials generate all the symmetric polynomials. But here, why we don't use en? It's because en is 1. En is 1. So this is why we just use n minus 1 of the first n minus 1 elementary symmetric polynomials. And this guy is unique. So now we have this polynomial, and we call this maybe SL1 Chebyshev polynomial. Okay, so now let's look at the Frobenius homomorphism for the skein algebra, SL1 skein algebra. Okay, so assume this guy is a unity. So now, we assume D is 1. I mean, of course, originally in this paper, we don't have this requirement. But in this talk, we only care about this case. So in this talk, we're only interested in this case. In the case when D is 1. And S is a punctual surface, then there's an algebra homomorphism. Phi, from here to here, we have the same root unity assumption, same convention. Here, I'm a little bit cheating. Actually, the map is not from the SL1 skein algebra. It is not for the SL1 skein algebra. It is for the SL1, the quotient of the SL1 skein algebra. We have the quotient, the kernel of something, of something called the splitting map. But people believe that this quotient equals this SLN skein module. It just means that kernel should be trivial. Because, I mean, I don't want to explain this quotient. It is not so relevant to this talk. So let's just use this version, a cheating version. But it should be true. So a Frobenius map is from this guy to this. I mean, it looks like the Goncharov algebra, the balanced Goncharov algebra. The balanced Goncharov, the phi is from also the z quantum torus for phi to the z quantum torus for omega. Here also the same. SL1 skein algebra for omega. Of course, here we use omega bar. To the SL1 skein algebra, not omega. It is from the SL1 skein algebra for the eta to the SL1 skein algebra for the omega. This is the Frobenius map for the SL1 skein algebra. We have the following property. The image is in the center. So why the image? I mean, for the Goncharov algebra, not all the images are contained in the center. It is something like we use a D, but here D is 1. If D is 1, the sub-algebra we defined previously, just the whole algebra, because now D is 1. So then for this guy, the image of the Frobenius map is contained in the center of this guy, of the SL1 skein algebra. And also for any embedded oriented curve C in this S embedded, so it just means there's no crossing. So there's no this kind of thing. And then we have this. The omega maps CK to be this. So what is CK? So CK is obtained by replacing C with this picture. I mean, C is just a circle. I just replace this circle with this. I think you can imagine it. Actually, to define the CK, actually we need some scalar multiplication, but not important. Yeah, just imagine CK as we replace CK with this picture. So, for example, if you have a CK here, of course, but here now we shouldn't regard this as a puncture. We regard this puncture as topology. It just means inside of this puncture, there are a lot of topologies. If so, then you can imagine the picture. Not just one puncture, any topology inside of this puncture. So we have this property for the Frobenius map. And so the reason why the Frobenius map is important is because, first, it is because it can give us a lot of central elements of the SL skein algebra. Actually, now also we have two types of the central elements. So one is one central element. One type is this alpha pk. Is this guy alpha pk? Another type also like the quantum torus. Another type is the image. Is contained in the image of this phi, this Frobenius map. Actually, of course, we expect that this is the whole center. I mean, the whole center of the SL skein algebra is generated by the alpha pk and the central elements contained in the center of the Frobenius map. We expect this is true. Until now, we can only prove for SL2 and SL3, but for general SLN, we don't know how to prove that until now. Okay. Now let's look at the representation, the irreducible representation of the SL skein algebra, also at the root of unity. So rho is an irreducible or finite dimensional irreducible representation, the SL skein algebra. And then for nx, also we assume that D is 1. For nx in the SL skein algebra, for the eta, then we have similarly, we have this, right? Because this guy is central, and then we have a complex number, R rho x. And also, for every alpha pk, it is also central, and then P maps this guy to scalar multiplication SPK. And like the balanced Fock Goncharov algebra, R rho is an algebra homomorphism, and also there's some relation between R rho and SPK. So then we have this relation. I mean, R rho alpha pk equals to this. This is the definition for R rho. And here for this, it comes from this property for the Frobenius map. So the Frobenius map maps alpha pk to be this. Because rho is an algebra homomorphism, you can just move rho inside of this polynomial. So then it will give us, because rho maps alpha pk to SPK times identity, then we have this. So compare this guy and this guy, we will get our rho maps alpha pk to be this. So now, also an irreducible representation of the skein algebra gives us also two data, the algebra homomorphism R rho, and also alpha SPK. And the relation between these two data is this. I mean, just like the balanced Fock Goncharov algebra, we should ask, if we have two such a data, can we get the irreducible representation? And also, actually, we call this two data the classical shadow of this rho. And now we're gonna look at how, if we have such a data, can we find an irreducible representation such that whose classical shadow is these two data? The answer is partially yes. Until now, the answer is only partially yes. It should be yes for all the cases. But until now, we can only prove something like that for if we give some requirement for this R rule, then we can find an irreducible representation of the rule. So now let's look at, now let me introduce what is the restriction for this R rule. Let S be a punctual surface with triangulation with a triangulation lambda. Then the algebra homomorphism, this is the quantum choice map. The quantum choice map for the eta, it is not for omega, induces a map from this to this. Actually, this map should be, actually, this guy is the algebraic right. This guy is also an algebraic right, because this guy is a commutative algebra. They're also domain, they're also finite generator. So now we have this map, trace star. Okay, so here is the theorem for the irreducible representations for the S7 skein. Still, root of unity assumption, and D is 1. And G is a punctual surface with a triangulation lambda. So the restriction on our rule, or the restriction on F, is that F is contained in the image of this trace star. And S, Pi, no restriction. But of course, we have this relation. We must have this relation. We have this relation with F and SPK. So if so, and then we can find an irreducible representation of the balanced Fock-Goncharov algebra rule bar, such that the classical shadow of any irreducible sub-representation of this rule. So what is rule? Rule is the combination of this guy. First, this is the quantization map. This is rule bar. We just pull back the rule bar to the SI1 skein algebra using the quantization map. So then rule is a representation of the SI1 skein algebra. And then it says that this theorem says that then the classical shadow of any irreducible sub-representation of this rule is this guy. So now we can find such an irreducible representation. But of course, but sadly, we cannot prove that it is unique. We expect that it should be unique for most of F. And also, for most of F, this rule, it should just be irreducible. So then it should just be irreducible. Yeah, but now we cannot prove this. And until now, we can prove such a thing for SL2 and SL3, but we cannot prove this for general SL1. And also, actually, we should expect that we can remove this constriction. Just for any F and S, we can find an irreducible representation whose classical shadow is that. But maybe this irreducible, but it is possible that this irreducible representation does not come from the irreducible representation for the balanced Fock-Goncharov algebra. Yeah, I think that's all for my talk. Thanks for your attention.